Okay. Now see here. Now this is 0 input response, which we already calculated. This is 0 input response for the same problem, because the complete time response, the question is, once again I am explaining here, complete time response for unit step input. Complete time response for unit step input. So a complete time response means it is having both 0 input response and 0 state response, which we already calculated 0 state response. Which we are already calculated 0 input response, and this is the 0 input response, right? Now next what should we do? 0 state response we want to calculate. What is the 0 state response? This is the 0 state response, inverse Laplace transformation of Si minus A matrix inverse into B into U of S. Okay, but you see Si minus A matrix inverse, which we already calculated here. See here, Si minus A. A is 0, 1, minus 2, minus 3. So S minus 0 is S. 0 minus 1 is minus 1, 0 minus minus is plus, S plus 3. So adjoint is this, determinant is this, and roots are S plus 1 and S plus 2. And matrix inverse is adjoint by determinant. And this is the Si minus A matrix inverse. Is it right or not? This is Si minus A matrix inverse. So, but what we required? Si minus A matrix inverse into, see here, Si minus A matrix inverse into B into U of S. So Si minus A matrix inverse is this one multiplied with B. B is 0 into, see, this is B. This is A matrix, this is B matrix, and this is C matrix, right? So this is B, 0, 5. C multiplied. Now this one into 0 is 0 plus 1 into 5. Therefore 5 by this one. Now this one multiplied with 0, 0 plus S into 5, 5 S by S. But where is S? Now here I am not writing S, because again it is multiplied with S. That's why it is coming S here. And this S is cancelled. Okay. So this is Si minus A matrix inverse multiplied with B multiplied with 1 by S. Now after calculating this, then do the partial fractions for this and apply inverse Laplace transformation is the 0. This is the inverse Laplace transformation. See here, this is the inverse Laplace transformation of this, and that inverse Laplace transformation will use the 0 state response. Okay, so we have to do the partial fractions for this, and after doing the partial fractions, apply inverse Laplace transformation, and the answer is this: 5 by 2 minus 5 into e power 5 by 2, and this is 5 into e power minus t minus 5 into e power minus 2t. Now the students, this is 0, what is this? This is 0 state response. This is 0 input response. Now first you note down, but what is a complete time response? The complete time response is the response, now C multiplied with x of t, C multiplied with x of t. Now x of t is nothing but 0 input response plus 0 state response. Okay. Now first you just note down this, then we will see. Okay, now you just see here. Now this is 0 input response and this is 0 state response. Now you tell me what is x of t? Now x of t, which is nothing but 0 input response plus 0 state response. Therefore, what is x of t? X of t, which is nothing but now 2 by 1 matrix, 2 by 1 matrix, direct addition. So 2 into e power minus t minus 5 into e power minus t. Therefore, 5 by 2 minus 3 into e power minus t. Now e power minus 2t, e power minus 2t. Therefore, 5 by 2 minus 1. So plus 3 by 2 e power minus 2t. Next, 5 into e power minus t minus 2 into e power minus t. 3 into e power minus t minus 3 into e power minus 2t. Now addition, 0 input response, 0 state response. I just add these two is x of t. This is the x of t. Note down this. Now, y of t, what is y of t? C into 0 input response plus 0 state response is nothing but x of t. So what is y of t? Y of t is the complete time response, which is equal to c is 0, 1 into x of t. What is x of t? X of t is this 5 by 2 minus 3 into e power minus t plus 3 by 2 into e power minus 2t. 3 into e power minus t minus 3 into e power minus 2t. So now what is y of t? Now this is y of t. Finally, this is 1 by 2. This is 2 by 1. So only 1 by 1. So this is 0 into something. This is 0. Now 3 into e power minus t minus 3 into e power minus t. This is the complete time response. This is the complete time response for unit step input. Okay, this is the way how to solve the question. This is the complete time response for unit step input. Note down. Okay, this is one question. Now he is asking complete time response for unit step or complete time response now for the system. So based on the input availability, based on the B matrix availability, then the complete time response may be 0 input response plus 0 state response or only 0 input response. Okay. Now, so then what type of another questions? Okay, the another questions are controllability and observability. Controllability and observability. Now, what is controllability? First, you see the definition of controllability. What is a controllability? Controllability means we want to, a state space model is said to be controllable if it is possible to transfer the initial state to any other desired state within finite interval of time. Within the sufficient amount of time, within the limited time, the initial state is to transfer any other desired state, any other required state within an interval of time, then that state space model is said to be controllable. Otherwise, it is not controllable. Okay. So, if it is not possible to initial state to any other state, it is not controllable. If it is possible to transfer the initial state to any other state, then this is nothing but the controllability. Sir, then what is observability, sir? What is observability? The observability is possible to get the initial state, from the output. If it is possible to gain, if it is possible to get back the initial state from the output, then that state space model is said to be observability. If it is not possible to get the initial state from the output, then it is not observable. Understand or not? So, if you observe here, this is the controllability and this is the observability. A scientist called as Coleman. So, he is finding two matrices. One matrix name is controllability matrix. Another matrix name is observability matrix. Now, he is defining a two matrices. One is controllability matrix and another one is observability matrix for verifying the controllability and observability of the state space and state space model. Understand or not? So, if you observe controllability, just listen carefully. Controllability definition. I want an initial state. I want to transfer the initial state to any other state. So, it is totally talking about state to state, initial state to any other state to initial state. Okay. So, according to Coleman, the observability matrix is, only deals with the state equation, only deals with state, because initial state to any other state. Therefore, according to Coleman, the observability matrix is B, AB, A square B, and so on, A power n minus 1 into B. Okay. So, this is the n is same as it is. N is order of A matrix, or n is the number of state variables, or order of transfer function, or order of differential equation, or number of integrator blocks, or number of storage elements, and everything. Okay. So, this is a controllability matrix. Now, based on N value, controllability matrix is limited. So, determine the controllability matrix determinant whose determinant is not equal to 0, then this is controllable. If the determinant of controllability matrix is not equal to 0, then it is not possible, means not controllable. Now, similarly, observability. So, possible to get the initial state from the output. So here observability is dealing with two, output equation as well as state equation. Therefore, according to Coleman, the observability matrix is C transpose, A transpose, C transpose, A transpose whole square into C transpose, and so on, A transpose whole power n minus 1 into C transpose. Same, n is same, order of A matrix or number of state variables or anything. So, if the observability matrix determinant is not equal to 0, then it is observable. If the observability matrix determinant is equal to 0, it is not observable. Clear or not? Okay, note on this. Clear or not? Okay. Now we'll verify by using one problem. Okay. Now, by considering the following state space model, verify controllability and observability. By considering the following state space model, verify controllability and observability. Now see here, to verify controllability and observability, we required A matrix, B matrix, C matrix, all are available, and A matrix order is 2 by 2, n by n. Therefore, what is n? Now n value is 2. Am I right? Not. Now n value is 2. If n value is 2, so 2 minus 1. What is 2 minus 1? AB. So this is the controllability matrix. Boundaries are now restricted to this. So now, what is B matrix? What is B? B is nothing but 0, 1. What is AB? Now first we want to find AB. What is AB? A into B, which is nothing but 0, 1, 2, minus 3. B is 0, 1. Therefore, what is the answer? 0 plus 0, 0. 1 plus 1, 1. 2 plus 0, 2 into 0, 0. Now, minus 3 into 1, minus 3. Therefore, which is nothing but 1 minus 3 is AB matrix. 1 and minus 3 is A. So now this is the controllability matrix, order is 2 by 2. Now find the determinant of controllability matrix. Now this is the 2 by 2 matrix. What is the controllability matrix determinant? Now the controllability matrix determinant is AD minus BC. AD minus BC minus 1, which is not equal to 0. Therefore, it is controllable. It is controllable means it is possible to transfer the initial state to any other required state. Now, similarly verify observability, same. A matrix order is n by n, 2 by 2. So, n equal to 2, 2 minus 1, 1. So, now the observability matrix boundaries are up to here. Now, what is C transpose? 1, 1. Now, we want to find A transpose into C transpose. What is A transpose? 0, 1, 2, minus 3. What is C transpose? C transpose is 1, 1. Now 0 into 1, 0, plus 2 into 1, 2, 1 into 1, 1, minus 3 into 1, minus 3. Therefore, which is nothing but 2 minus 2 is the resultant of A transpose. 2 minus 2. So this is also a 2 by 2 matrix. Now find the determinant of observability matrix. Now what is the observability matrix determinant? The observability matrix determinant is AD minus BC minus 2 minus 2 minus 4, which is not equal to 0. Therefore, it is observable. Possible to get the initial state from the output. It is possible to transfer the initial state to any other desired state. Okay? No doubt. Clear or not? This is one question, controllability and observability. So in all the analysis topics, I just give the controllability and observability and state transition, zero input response, zero based response, like that. Okay. Now these are the generally asked questions in the state space analysis linked answers bit. Okay. So now we'll solve one problem. No doubt. By considering the following state variable, by considering the following state space model, which is 0, 1, minus alpha, minus 2 beta, x1, x2, plus 0, 1. Now y is 1, 0, x1, x2. Now this is the state space model which is given to you, and what he is asking is determine damped frequency of oscillation and determine damping factor and natural frequency of oscillation. This is the question. Okay. Now once again I just dictate the question. By considering the following state space model, this is state equation, output equation, and determine damping factor and natural frequency of oscillations, and these are the options. This is damping factor and natural frequency of oscillations. Okay. So damping factor and natural frequency of oscillations are the parameters of the second order system what we have studied so far. Okay. So now I want a characteristic equation. Okay. Now the standard characteristic equation is nothing but, what is the characteristic equation generally? The characteristic equation is nothing but 1 plus g of s h of s is equal to 0. Now s square plus 2 zeta omega n into s plus omega n square equal to 0. This is the characteristic equation of a closed loop control system. Now you tell me what is the characteristic equation of a state space model? You can find directly, and most of the students are doing a lengthy analysis, find the transfer function, and so many of you are doing is mistake, and some of you are using this formula C into Si minus A matrix inverse into B plus D, like that you are doing this. Why? What is the purpose of that? Even if you do this method, then you want to see the denominator polynomial, because the denominator polynomial is called as a characteristic equation. That characteristic equation you can find directly without doing all these things. Am I not? Now that characteristic equation directly. Now the characteristic equation. What is the characteristic equation of a state space model? The characteristic equation of a state space model is determinant of Si minus A equal to 0. So we have to find first Si minus A. S 0 0 S Si minus A, because A is 2 by 2 matrix, 0 1 minus alpha minus 2 beta. This is Si minus A matrix. Si minus A matrix equal to S minus 0 0 minus 1 minus plus alpha S plus 2 beta. Now this is Si minus A. Now determinant of Si minus A. Now this is the 2 by 2 matrix. So what is the determinant? Determinant of Si minus A equal to 0. Therefore AD minus BC, S into S plus 2 beta, AD minus BC minus plus alpha equal to 0. Therefore S square plus 2 beta S plus alpha equal to 0. This is the characteristic equation of a closed loop control system. Characteristic equation of a closed loop control system. Now what is the characteristic equation? Now what is the characteristic equation of a state space model? The characteristic equation of a state space model is determinant of Si minus A equal to 0. How much you are getting? Now you are getting S square plus 2 beta into S plus alpha equal to 0. This is the characteristic equation of a closed loop control system. This is the characteristic equation of a state space model. Then if you compare these two, omega n square equal to alpha, therefore omega n, which is equal to root alpha. Root alpha is only these two options. Therefore this is the wrong option, and this is also the wrong option. Now 2 zeta omega n, which is equal to 2 beta, 2 cancel, 2 zeta omega n is nothing but root alpha, which is equal to 2 beta. 2 cancel, zeta equal to beta by root alpha. So beta, this is only root beta round, therefore this is the correct answer. This is 2019. This is the recent GATE exam. 2019 GATE paper, 2 marks question. Clear or not? Okay. Now definitely a 2 marks question from the state space analysis. Then for the past 10 years you take papers, and which will be the question. Right? Now these are the questions generally what he is asking. Okay. Then we'll solve one more last question. By considering the following state space model. Now this is the state space model. X dot, which is equal to 0 1 0 0 0 1 0.5, 1, 2 into x plus 0, 0, 1 into u, where u equal to 0.5 minus 3 minus 5 into x plus some k. Now see here, and what is the question? What he is asking? He is asking find eigenvalues. Find eigenvalues. What is asking? Find eigenvalues. Now students, now this is A, this is B, this is C. If you are writing like this, it is 100% wrong, and this is not the A. So that's it. That is the reason why you can get the wrong answer. So here this is u equal to something he is given in the question. First you just read the question. So this is u, this something into x. So this x and this x is again added. So you just see here, you can understand easily. What is u here? You write u. What is u? Now which is equal to minus 0.5 minus 3 minus 5 into x plus k. Now plus 0. This is 3 by 1. This is 1 by 3. Then multiplication is possible, and again the answer is 3 by 3 matrix. 0 into 0, 0, 0. 0, 0, 0. Minus 0.5, minus 3, minus 5 into x. Now again here is there 0, 1, 0, 0, 0, 1, 0.5, 1, 2 into x. Here is important. Here is, this is x plus. See here, this is 3 by 3 into x plus 3 by 3 into x. Then that will become the a value actually. Understand or not? So plus 0, 0, 1 into k. So what is x dot? X dot is 0 plus 0, 1 plus 0, 0 plus 0, 0 plus 0, 1 plus 0, 0.5 minus 0.5, 1 minus 3, 2 minus 5 into x plus 0, 0, 1 into k. Now this is nothing but matrix A. This is nothing but matrix A. Now once the matrix A is given, now you find characteristic equation. Now the characteristic equation is determinant of Si minus A equal to 0. Determinant of Si minus A equal to 0. This is A, and you use and Si minus A equal to 0. Now that roots is nothing but eigenvalues. From here you can get the eigenvalues. And this is the A matrix, not this. Don't take this is A, wrong. Answers are getting. This is the A. Simplify that. Clear or not? Okay, no doubt. Okay, now this is the state space analysis. Okay, then definitely 2 marks. Okay, in the next session we will see the another two.